we're basing it upon a p-value that we get from a statistical test. And this is to test a hypothesis, okay, to test the null hypothesis in particular, okay. So we do our study, we collect our data, and either there's no effect of the treatment, for example, or there is an effect. So if there's no effect, then the null hypothesis is true for this particular study, or there is a treatment effect and the null hypothesis is false, all right? So that's for a particular study, okay? And we do the analysis, we get our p-value. If we get a p-value that is less than 0.05, then we reject the null hypothesis. We say, yeah, it looks like there's something happening here. The treatment is doing something. So, and I can use, okay, so I went through what the type 1 error is here. This is when we reject the null hypothesis. When the null hypothesis is true, we try and make this probability quite small because we don't want to have lots of false positives in the literature. We don't want to have people publishing stuff which is not replicable and misleading. Okay, so if the null hypothesis is true, then we can make a type 1 error. There's a 5% chance if we use alpha of 5%. Fortunately, there's a 95% chance that we make the right decision, okay? If the null hypothesis is false, then if we reject it, we are making the correct decision. And however, if we don't reject it, then we are making the type 2 error. That's represented by beta. Okay, and it's the same thing here. I was using this example, framing it in terms of a criminal court. So you've got a defendant in front of the court. Is the defendant, this particular defendant, innocent or guilty? Okay, and that's true. Either they've done it or they haven't done it. Okay, what happens to them then is determined by the cells within this table. Are they charged falsely? If so, they were innocent, right? If they were guilty, then that's the correct conviction and so on. So we've got alpha and beta here in the same way. And I was just framing it. I did the same with the prospective surgeons. I did the same with the doormats, okay? You've got a particular doormat coming along the conveyor belt. Either it's good or bad, okay? If it's good and you fail it, that is your producer's risk because you're throwing away a good mat which could have earned the company money. On the other hand, if you pass the mat and it happens to be a bad mat, then that's the consumer's risk. And when we switch these around where health and safety, health in particular, is a big issue, like the aortic valve, then we need to be very careful. We want to minimize the patient's risks. So if a patient dies as a result of a faulty aortic valve, then this could mean a big financial loss to the company. So they want to reduce the patient's risk here. There's going to be, to reduce the patient's risk, there's going to be producer's risk. That's probably, they will need to throw away a lot more valves, which actually are good, probably, because they're being very fussy about the valves. So it's a trade-off between these two things, patient's risk, producer's risk, type 1 error or type 2 error, okay? Okay, so let's, a question already, fast, okay, yes.
She's asking if there's a fixed value for beta, if alpha was 0.05.
It's a good question. Only when we're planning a study do we fix beta. We try to fix it to be quite small. We make it about 20% or smaller, okay? But we can't actually fix it. It's something that we work to when we're working out our sample size. That's the type 2 error probability that we try and use. So I'm going to get onto that soon, so that'll make more sense. Okay. So I'm just going to go through this example here. where we've got, okay, so this is where the null hypothesis is true. Okay, so the two means, mu0 and mu1, they're lined up. They are in the same position. There's no effect. Okay, and what we have is this is the sampling distribution for the mean as before. So these two means are the same. And we've got these little red tails. These are the tails where if you get a result out beyond these, in these red regions, then you would reject the null hypothesis. So this is where the null hypothesis is true, okay, as I've emphasized here. So where mu1 is equal to mu0. You've seen this diagram already, so I'm, well, similar to this already, so I'm just repetition. What about, what's happening? Okay, what about if H1 is true, in other words, H0 is false, so actually mu1 is in a different position, then, can I move this thing? Can I move this out of the way? How can I get this out of the way?
Just grab it.
Grab it and, yeah, move it around, but it's still in the way. Can't I minimize it or something? No. Okay, thanks. All right, so what we've got here is where the alternative hypothesis is true. In other words, mu1 is up here, okay? Where this dashed line is, that's where the true value for mu1 is. In which case, when we select from that population a sample, it will be under this curve and it should be close to mu1. Okay, so you can see there's this ghost of the null hypothesis here. It keeps coming back, this thing. Okay, then I can't see that. Okay. All right, okay, that's better. Okay, so you can see the ghost here of the null hypothesis. And you've got to remember that we always do our test assuming that the null hypothesis is true. Of course, the null hypothesis may not be true. In fact, usually it's wrong, okay, it's not true. It depends how you define your null hypothesis. Okay, so here it is, and these pink regions, these are the rejection regions, alpha over 2, that's 2.5% in each. So you can see that if we look at this pink area here, anything above this point here, that we would reject the null hypothesis, and it looks like it's more than 50% because 50% is where this dashed line is. Okay. So this is when the null hypothesis is false. That's what I was showing in this slide here. And I'm just highlighting the regions now. So what's this blue region? The blue region is, okay, the red region is the significance level, a type 1 error, all right? So the blue region is, it's beta, yes, correct. This is beta. So we've got mu1 is greater than mu0, in other words, it's here. And then the remaining area here, the rest of this curve, this is known as the power of the test, okay? So as I was saying previously, it looks like more than 50%. Okay, it may be 60%. If it's 60%, then beta is 40%, which is quite high. In other words, the power is low. If it's only 60%, that's quite weak power. That's not a very good chance of getting a statistically significant result with p less than 0.05. Okay, so how can we increase statistical power? Any suggestions here? Sorry? Decrease beta. How would we decrease beta? Huh? You can't just say, I want beta to be smaller. You can do that with alpha. You can have alpha whatever you want. You can have it 1%, you can have it 5%, you can have it 10%, whatever, but you can't actually do that with beta in the same way. You're not specifying beta unless you're doing a calculation of sample size. So we need some way of reducing the overlap. If I go back to these diagrams here. Yes, that is one way. Okay, increasing sample size. Okay, and if you look at this diagram, if we were to have a larger effect size, so let's say mu1 was to move over here, then alpha stays in the same place, but beta would get smaller, okay, as that curve moves over. So I think I can demonstrate this here. So this is what we saw in the previous slide, okay. What we had was, as I say, about beta of about 40%. But if we make the effect to be larger, so there's this, we move mu1 over, then you can see, drawing this line down here, beta becomes a lot smaller. So instead of 40%, it may be like 10%, okay? Which is okay, that's improved the situation. If it's 10%, then the power is 90%. Okay. Okay, and then the person correctly said, if you increase the sample size, that's fine. Actually, just going back to this, how would we increase the effect size? Sometimes this is quite difficult to do. It depends on your intervention. Let's say you are using a particular therapy, okay? How do you make that therapy more effective? There may be some means, but sometimes it's difficult. It may be easier if you think about in administering a drug, you could, instead of using a small dose, use a higher dose. That may be a way of increasing the effectiveness of the drug and increasing the effect size in your study. However, of course, if you use larger doses, then you may get more side effects. So there could be problems there. Okay, so what happens here, this is the distribution from the previous slide. You can see where we've got the beta at about 40%, it's very large, okay? If we increase the sample size, the means stay in the same place. Obviously, mu1 is in the same place. You can see this dashed line continues down. But they become, as you remember from the central limit theorem, they become narrower. The sampling distribution becomes narrower. If it's narrower, then there's less overlap between this sampling distribution for mu1 and the null hypothesis sampling distribution. So you can see now this is down at like 5%, okay, just by increasing the sample size. We're not changing mu1 by the sample size. No, you can see mu1 is staying in the same place. What's happened is that because we've increased the sample size, the standard error has got smaller, so the sampling distribution becomes narrower. This goes back to our sampling distribution of the mean lecture. Is that okay? Right. Okay. So statistical power, as you know, as I've been explaining, beta is the probability of making a type 2 error. This is of not rejecting the null hypothesis when it is false. Okay. So phrasing this more positively, we can think of this as the probability of rejecting, if we subtract it from 1, okay, beta from 1 minus beta, we will get the probability of rejecting H0 when it's false. So this is the probability of correctly getting a significant result. Okay, so here it is. If null hypothesis is false, here's beta, then the power is 1 minus beta. So that's what I've been saying. power only makes sense if the null hypothesis is false. If the null hypothesis is true, then there's no point in thinking about beta. You can't make beta error. You can't make a type 2 error if the null hypothesis is true, all right? Remember, these two situations are mutually exclusive. Either null hypothesis false or it's true. Okay. You can only make the error depending on which is the case. Okay. So the probability of correctly rejecting H naught is given by 1 minus beta, and this is the statistical power. So if the power of a statistical test is high, then there's only a small probability of a type 1 error. Okay. So when we plan a study, and this is where I say you can specify beta, or the power, which is 1 minus beta, is when you're trying to estimate the sample size that you need for your study. And typically people go for about 80% or more. Okay. So specifically what we have is the probability of rejecting the null hypothesis when the null hypothesis is false. So this is what the power is. Okay. So calculating power and sample size in practice. Now you can do the calculations by hand using Z, and we could go through that. It's slightly involved, but it's easier just to use an application which is available online. So G star power is quite good. There are plenty of other ones. It depends what you're doing. G star power is good for studies, experimental studies, that sort of thing. But there are other ones if you're doing surveys which address those issues for sample size. Okay, so we can work out the power and sample sizes for many different statistical tests, such as T, ANOVA, chi-square. Okay, you haven't done these yet, but you'll be doing T and ANOVA next week and the week after. Yeah. Okay. This one? In what way? Just want me to read it again, or what? What's there to explain? It's it explains itself. What is it that they don't understand? Is it the last one? Probability of rejecting the null hypothesis, conditional on, that's what the vertical line means, conditional on the null hypothesis being false. Because you can only calculate power, as I say, when the null hypothesis is false. If the null hypothesis is true, then you cannot calculate power, however much you would like to do that. Why is higher power good? Yes, higher statistical power is good, okay? The reason is that if you do a study and you have low power, then, and there is an effect there, all right? Your new therapy that you're assessing actually does something. But if your power is very low, let's say it's only 20%, okay, 20% power, that means beta is 80%, then you've only got a 20% chance of getting a statistically significant result, okay, which is not very good. You may have spent a lot of time collecting the data, analyzing it, and then, yeah, it comes out not statistically significant. Doesn't mean there's nothing there. There is, I've told you there is an effect, but because your power is so low, you cannot detect a statistically significant result. When would that happen? When do you think that could happen? When it's not significant, then your p-value is greater than 0.05, all right, remember? So this goes back to a slide from last lecture that I showed you, the confidence intervals lecture, where we've got okay, when the effect size is small? Sure, yeah. Let's say it's big though. Let's say the effect size is big and it's still not statistically significant. What's going on? What's the problem with your study? Higher p-value. Sorry, we can't play with a p-value, right? P-value is pretty much fixed at 0.05. Sorry, some people do play with it. There's a move to make it 0.005, all right? Make it 10 times smaller. But for this course, we're going to stick with 0.05, and most journals will publish if you have a p less than 0.05. Okay, so what we have is where we've got an unsignificant result, but there is an effect. So let's say the effect size is large, but the p is also large, okay? So how has this come about? Okay, any response? No one shouting? Talking?
P is very large.
Yes, beta is large. Type 2 error, yes. So why is our type 2 error so large? Okay. It's probably because our sample size is too small. We've done our study with 3 patients, okay? You're not going to get a statistically significant result if you use 3 patients and you're testing a new therapy, all right? That's going to be too small. So your beta will be massive. Your power will be small. You could get a statistically significant result, but the chances of that happening are only 20%. Okay. All right. So can we move on, or does that satisfy that questioner? It disappeared. Okay. Right. So where did we get to? Yeah. So when we do this in practice, actually we can use an application, and there is a module in Jamovi which does this quite nicely too, but only for a limited number of tests. So probably more will become available. Using G-Power, it's nice. So what I've done here, this is just a screenshot. I'm using 2 tails. That's what we should usually do. I'm using an effect size of 0.5, which is a medium effect size. Okay, so you can see here 0.5. Now my alpha I specify as 0.05. This is a default. Okay, and I've specified a power here of 0.8. I said 80% for power. That's what we specify. If you then click on calculate, it gives you these things on the right. Okay, so it says we need to have 64, this is for a 2-group comparison. We need to have 64 patients in each group. Okay, now it's done a nice little diagram up here for us. The red is the null hypothesis. It's just like what I've been showing you, right? And the blue is for an effect size of 0.5. Okay, so you can see that where the line is drawn for the alpha over 2 here, that determines the size of beta, okay? And this is 20%, okay? Because I specified 80% power, so it's going to be 20%, okay? So this remaining area is 80%, which is what I specified. Now I can show you this in Jamovi. Let's do exactly the same, actually. Got Jamovi here. I need to install it first. So let's go and install it. Okay. So it's a module, library. Here we are, J Power. Okay, so we install this. All right. So where is it? It's here. So if I click on this, and I'm going to do independent samples t-test, it's like a 2-sample z-test. Okay, so minimal effect size is 0.5, that's fine. Now it's saying default 0.9. I'm going to change that to 0.8. Okay. And relative size of group 1 to group 2 is 1. So it just means the same size in each group. You could specify half the number in one group compared with the other group if you wanted to. The alpha, I've got 0.05 and tails 2 tailed. So it's a 2-tailed test. Okay, so let's see. So here's the calculation. So it gives me the same number in the 2 groups, 64 in each, all right? And it just repeats the settings that I've got here, effect size 0.5, power 0.8. Okay, so it's got quite a nice plot here, which shows that if I was to reduce the sample size, then I would need a larger effect size to get the same power, okay? So you can see if I want to get if I want to use only like 10 in each group, which is going to be about here, this is on a kind of funny log scale. 10 in each group is going to be, I'm needing an effect size of more than 1, maybe 1.4, something like that. Okay, so high power is shown is in yellow, marginal about 0.8 is in green, and then you can see lower and lower power down to 0.2 and below. Okay, so as I decrease my sample size for the same level of effect size, 0.5, you can see that the power decreases looking at these colors. It's kind of nice contour diagram. I think I can do another diagram too, which is, yeah.
I was asking why it's having a very large data that.
Because it means low power, because power is 1 minus beta. Okay, so if your beta is 80%, then power is only going to be 20%, which is not good. Okay, power demonstration. Yeah, here we go. It's got the same as what we had with G-star power. It's the same diagram. This is the null hypothesis. This is the alternative hypothesis for an effect size of 0.5. And this area here is 20%. And if I have 64 patients in each group, so a total of 128 in my study, then I would have an 80% chance of getting a statistically significant result. Of course, this assumes that the effect size is 0.5. If the effect size is larger, then my power increases, okay? So just shown in this diagram, if as my effect size increases, let's say it goes to 0.5, and for the same number, this is for 64, it goes right into the yellow area, which gets closer and closer to 1. So I might be having a 99% chance of getting a statistically significant result. In other words, beta is then just 1%. Okay. The other one, I think, is this power curve. Let's see.
Someone's asking the alpha here is not 0.05, right?
Yeah, alpha is 0.05 for all of this. Yeah. What changes is the power, and if you subtract that, if you subtract from 1, then you get beta, all right? So if the power is 0.8, then beta is 0.2. Okay, so this is the power curve. Again, this sort of log scale here. If you've got your sample size, as it increases, you can see the power increases. This is for a delta or effect size of 0.5. So you can see with, as I said, rather small sample size, let's say you only had 11, then our power would be 0.2. Okay, so there's different ways of showing the same thing. I quite like this these plots. They're useful. Okay, and here it's just explaining that if you've got less than 50% power, then you're 50% going to miss what you're trying to find. If it's between 50 to 80, it's a reasonable chance. If it's between 80 to 95, it's probably you will detect it. If it's greater or equal to 95%, then you will almost surely detect. And these are the effect sizes here. So we specified 0.5, so up to 0.5 here is 50 to 80%. And then from 0.5, 0.499 up to 0.642, that's the size of the effect, you have an 80 to 95% chance. Okay, let's go back here. And what are the factors that affect power? Well, we've already talked about two of them, all right? The first is how large the effect is. So if there's a large effect, then the power will be greater. Okay. The second factor is the sample size, all right? If you've got a large sample, you will have a more powerful statistical design. And this is actually something that we have most control over. So instead of collecting just 3 participants or patients, then collect 30 or 40. It's more time, that's true. You may be limited by your funding or your time, but we do have some control over that. As I say, in many cases, we can't actually control the effect size. If it's a particular treatment, let's say a type of surgery or something, and we're seeing the effects of that new surgery compared with conventional surgery, then we can't actually change that effect size, not easily anyway. Okay, there are other ways, and that's by decreasing the variability in the sample. So for example, this is what a lot of people do, they restrict the age range of their participants. So instead of taking from children up to 100, they would restrict it to adults, say from 18 up to 45, something like that, okay? If you do that, then you're decreasing the variability. You're not going to have the very young, and you're not going to have the frail old people in your study. These will introduce more variability. You can do other things. So, for example, you could just do your study in women, okay? So you're testing a new drug in women for Alzheimer's, and it looks like it works nicely. You've reduced your variability because there's a difference between men and women in the way they perform. So the problem with publishing this study is that, okay, you know that the drug works in women, but what about men? You don't have the data for the men. So sometimes we have to we can't reduce the variability too much. Okay, there's another way, and I think someone here suggested that, and that was by increasing alpha or changing alpha. I've got to say you can't usually do this. It's kept at 0.05. It's not practical to manipulate this factor. If you increase alpha, okay, increasing alpha will decrease beta, okay. Let me just go back so I can show you that in the diagram. So in this diagram here, let's say we were to increase alpha, move this line this way, you can see that beta becomes smaller. So let's say I decreased, let's say I increased alpha to like, I don't know, 30% or something, then beta would be very small, okay? It would only be like 0.1 or it would be less than 0.1 or 10%. So there is a problem in that if you increase alpha, obviously what you're doing then is, if the null hypothesis is true, then you're more likely to make type 1 errors. Okay? People won't believe you unless you get p-values less than 0.05. I guess that's the method, that's the truth of it. The type of statistical test can make a difference. I'm going to be covering parametric tests, and I think later in the semester you will have a lecture on non-parametric tests, which can be more powerful in some situations. But in general, if the assumptions are satisfied for a t-test, then parametric tests are more powerful. Okay, so statistical power. So we suggest using, specifying, if you're going to work out a sample size, a power of 80%. Okay, we need to do this before we start the study, and we can do our calculations based upon an effect size that comes from other research or from a pilot study. So you might just collect data from 10 patients, and the mean of your data will tell you roughly how large your effect size is. And then from that, you can work out how many patients you need in your study. The other way is to specify minimal effect size, and I've talked about this already. So what is the treatment effect that would be of minimal interest to you? So the example I've used before is reducing blood pressure. Is it going to be 5 millimeters of mercury or 10 millimeters of mercury? I think 1 millimeter of mercury would be too small. You probably want to specify something like 5 or 10. I don't know. It's an expert decision that needs to be made on medical grounds. Okay. So you can also work out power post hoc. Post hoc means afterwards. So you've collected your data, and then you work out, looking at the effect size, and then seeing what the probability is that you would get a statistically significant result. So you may have ended up in your study with a non-significant result. So then you can do a kind of post hoc power analysis and say, oh, damn, I just didn't have enough patients in my study. That's why I haven't got a result that is statistically significant. The power was only 30%. So you only had a 30% chance of getting a statistically significant result. This has been looked at in some areas like the social and medical sciences, and it's very depressing to see that these analyses consistently show that the average power in studies that have achieved statistical significance is about 50%. This is not very good. It's not good at all. They're lucky to get statistical significance. It's a bit like tossing a coin. It's a 50-50 whether you're going to get ahead, right? So they were lucky to get statistical significance. They publish. Just happened that the mean that they obtained was, or the variability was low. The mean was higher than expected. So average power should be much more than that. And as I say at the top of this slide, 80% is what we should be using. Okay. Yeah, I think that's it, isn't it? Okay. Any questions?